How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
Imagine a library that contains everything. Every book ever written, every poem, every scientific paper, every chaotic forum thread and emotional blog post. This is the diet of the modern artificial intelligence. We look at tools like ChatGPT or Claude, and we see a trajectory that points straight up. We assume that if we just feed them more data, they will become smarter, sharper, and more human. We assume the fuel tank is infinite. But there is a hidden limit to this growth, a mathematical wall that we are slamming into faster than almost anyone realizes. It is not a problem of computing power. It is not a problem of electricity. It is a problem of inbreeding. What happens when the smartest entities on the planet stop learning from us and start learning from themselves? Today, we are opening the black box of synthetic data and the existential threat of model collapse. To understand why the future of AI might not be an explosion of intelligence, but a collapse into nonsense, we first have to look at the magic trick as it stands today. We live in the era of the generative revolution. You type a prompt into a box, and the machine gives you a result that feels shockingly novel. You ask for a recipe for a cake that tastes like regret, and it gives you a poetic, culinary metaphor involving bitter chocolate and salted caramel. You ask it to write code for a website, and it structures logic with a precision that rivals a senior engineer. This feels like magic because it feels like creation. We look at the output and we see a spark of something new. We use these tools to draft our emails, to summarize our meetings, and increasingly to populate the internet itself. If you browse the web today, you have almost certainly read an article, a comment, or a product review written by a machine, and you probably did not even notice. The prose was clean. The grammar was perfect. The tone was confident. This is the golden age of the large language model. These systems are built on a very simple premise that we have discussed before, but it bears repeating. They are prediction machines. They are not thinking in the way you and I think. They are looking at a sequence of words and calculating, based on billions of examples, what the most likely next word is. To do this effectively, they need training data. They need examples. They need to see how humans use language in every conceivable context. So the companies building these models, OpenAI, Google, Meta, did the logical thing. They scraped the internet. They took the Common Crawl, a repository of petabytes of web data, and they fed it into the furnace. They fed it Wikipedia, Reddit, the New York Times, and the Project Gutenberg Library of Public Domain books. They fed it the collective output of human history. And it worked. The scaling laws, a concept observed by researchers like Jared Kaplan, suggested a simple relationship. The more data you feed the model and the more compute you throw at it, the better it gets. It seemed like a linear path to godhood. Just keep making the models bigger. Just keep feeding them more text. But here is where we hit the first wall. The internet is big, but it is not infinite. Specifically, high-quality, human-generated text is a finite resource. Some researchers estimate that by the year 2026, or perhaps a bit later, we will have effectively run out of high-quality public text data to train on. We will have read the whole library. There are no more books. So, the engineers and the data scientists looked at this looming shortage, and they came up with what seemed like a brilliant, elegant solution. If the model needs data to learn, and the model is really good at generating data, why don't we just use the model to create the curriculum for the next model? This is the birth of synthetic data. It sounds perfect. It is cheap. It is infinite. you can tailor it. If you need more medical textbooks to train a medical AI, you don't need to wait for doctors to write them. You just ask your current AI to generate 10,000 examples of medical case studies, and then you feed those examples into the next generation. It is a perpetual motion machine of knowledge. It is the snake eating its own tail, the Ouroboros. But when researchers actually tried this, when they took a model, had it generate data, and then used that data to train a new model, and repeated the loop 5, 10, 20 times, something terrifying happened. The models didn't get smarter. They didn't even stay the same. They broke. The grammar remained perfect. The confidence remained high. But the connection to reality dissolved. The models started to forget basic facts. They started to lose the nuance of human variability. Eventually, in the late stages of this loop, they collapsed into gibberish. One research paper described a model that, after several generations of training on its own output, began talking exclusively about jackrabbits. Another simply repeated a single phrase over and over. This phenomenon is called model collapse, and to understand why it happens, we have to strip away the sci-fi gloss of AI and look at the raw statistics underneath. We have to go back to the first principles of information theory and probability. Let's step away from computers for a moment and go to a photocopier. Imagine you have a beautiful, crisp photograph of a landscape. It has deep shadows, bright highlights, and subtle textures in the trees. You put this photo on a copier and you make a copy. The copy looks pretty good. Maybe it is 99% accurate. But if you look closely, the darkest blacks are a little gray. The sharpest lines are a little fuzzy. Now you take the original photo and you throw it away. You put the copy on the glass, and you make a copy of the copy. You repeat this process, generation 3, generation 4, generation 10. By the time you get to generation 50, what do you have? You do not have a landscape. You have a blurry, high-contrast mess of black blobs and white space. The detail is gone. The information has been destroyed. This is a physical analogy for a digital problem known as the accumulation of error. But in AI, the problem is more specific and more insidious than just blurriness. It is about the loss of variance. Think about a bell curve. Imagine we are graphing the height of all human beings. Most people are in the middle, average height. That is the hump of the bell. But then you have the tails of the curve. You have the very short people and the very tall people. The tails are where the outliers live. The tails are where the diversity is. When an AI model predicts the next word in a sentence, it is essentially looking at a probability curve. If I say, "The cat sat on the model looks at its training data. It sees that mat is the most common completion, chair is common, floor is common. These are the middle of the bell curve. But sometimes, in real human writing, the cat sits on the medieval tapestry, or the cat sits on the thermonuclear detonator. These are the outliers. They are rare, but they are possible, and they are what make human writing interesting, creative, and specific. Here is the crucial mechanism of model collapse. When a model generates text, it tends to play it safe. It favors the most probable answers. It gravitates toward the mean. It wants to be right, so it chooses mat far more often than it chooses medieval tapestry. Now imagine we take 1 billion sentences generated by this risk-averse AI, and we use them to train the next model. The training data for the second model is now biased. The tails of the distribution, the rare, weird, interesting outliers, have been chopped off. The dataset is narrower. It is more average. The second model learns from this beige dataset. When it generates text, It plays it safe within that already narrowed range. It converges even further toward the center. It shaves off the remaining outliers. If you repeat this loop, you trigger a recursive narrowing of the probability distribution. The variance of the model collapses. In the research paper, The Curse of Recursion, researchers Shumailov and his colleagues demonstrated this mathematically. They showed that without fresh data from the real world, without a fresh injection of human variance, the model mathematically must drift toward a zero-variance state. It becomes a caricature of intelligence. It is like a room full of people who only know how to make small talk about the weather. They speak perfectly fluent English, but they have nothing to say because they have forgotten that anything exists outside of sunny with a chance of rain. But wait, you might ask, why can't we just program the AI to be more creative? Why can't we tell it to choose the weird words sometimes? We do. There is a parameter called temperature that controls how much randomness the model injects into its choices. If you turn the temperature up, the model takes more risks. However, synthetic data breaks this too. Even if you turn up the temperature, the model can only choose from the concepts it understands. If the concept of a medieval tapestry has been statistically washed out of the training data in Generation 3, the model in Generation 4 simply cannot generate it, no matter how high you set the temperature. You cannot randomly select an option that no longer exists in your worldview. This brings us to a historical parallel that is uncomfortable but illuminating: the Habsburg jaw. The Habsburg royal family in Europe wanted to preserve their power, their purity, so they married within the family. Cousins married cousins, uncles married nieces. They created a closed loop of genetic material. They thought they were concentrating their greatness. In reality, they were concentrating their flaws. Recessive traits that would normally be washed out by a diverse gene pool were amplified. By the time of Charles II of Spain, the family line collapsed. He was physically disabled, prone to illness, and infertile. The line ended. Model collapse is the digital equivalent of inbreeding. When AI trains on AI, it amplifies the biases and the hallucinations of its predecessors, while shedding the healthy diversity of the real world. Let's look at how this manifests in different types of data, because it is not just text. It happens in images too. Researchers have run experiments where they ask an AI to generate pictures of faces and then train a new AI on those faces. In the first generation, the faces look like normal humans: diverse races, diverse ages, diverse bone structures. But the AI has a slight bias toward what it considers the ideal or average face, usually symmetrical, smooth-skinned, and vaguely celebrity-like. By Generation 10, the diversity is gone. Every face looks like the same airbrushed, racially ambiguous supermodel. The distinct features, the crooked noses, the interesting scars, the specific ethnic characteristics, have been smoothed away into a horrifying uniformity. Then the collapse deepens. The hands start to deform. The eyes stop looking like eyes. Because the model has stopped training on the reality of human anatomy and started training on its own flawed approximations, the errors compound. It is a game of telephone played by a billion-dollar neural network, and by the end, the message is lost. This deconstruction brings us to a profound realization about what we are actually doing with artificial intelligence. We often talk about AI as if it is creating intelligence from scratch. But the first principle here is that AI is not a creator, it is a compressor. Think of a zip file. When you zip a folder, you are using math to find patterns in the data and squish them down so they take up less space. When you unzip it, you get the data back. A large language model is essentially a lossy compression of the internet. It has taken the vast, chaotic, messy sum of human knowledge and compressed it into a file, the model weights, that can fit on a thumb drive. When you prompt the model, you are effectively asking it to unzip a specific piece of that knowledge. But because the compression is lossy, like a low-quality JPEG image, it doesn't unzip perfectly. It fills in the gaps with its best guess. When we use synthetic data, we are compressing a compression. We are taking the JPEG, saving it as a JPEG again, and then doing it again. Each time, we lose high-frequency information. In image processing, high-frequency information is the sharp edges and fine details. In language, high-frequency information is the rare facts, the unique turns of phrase, the creative leaps, and the messy truths of reality. The problem, and the reason this is a crisis for the tech industry, is that we need synthetic data to work. We are building bigger engines, and we are running out of premium gas. If we fill the tank with the exhaust from the engine itself, the car stalls. So, how are the engineers trying to solve this? They are trying to create smart, synthetic data. They are trying to build filters that can distinguish between good AI output and bad AI output, only feeding the high-quality stuff back into the system. But this creates a new paradox. To build a filter that can perfectly identify high-quality data, you effectively need a model that is already smarter than the data it is filtering. If you have a model that knows what is true and what is false, why do you need to train a new model? Furthermore, who decides what is high quality? If the filter prioritizes clean grammar and typical sentence structures, it will accelerate the collapse toward the mean. It will efficiently weed out the medieval tapestries because they look statistically unlikely. This leads us to the unseen giant. We have talked about probability, we have talked about inbreeding, and we have talked about compression. But the fundamental law governing this entire failure mode is not a law of computer science. It is a law of physics. It is the second law of thermodynamics, entropy. In a closed system, entropy, disorder, always increases. You cannot create order for free. You cannot create information out of thin air. Human data is low entropy. It is highly ordered. It is rich in signal because it is grounded in the real world. When a human writes a sentence, that sentence is the result of sensory experience, emotional processing, and interaction with physical reality. "The coffee is too hot" is a sentence born from the physical sensation of heat. It carries the signal of reality. AI data is disconnected from that reality. It is a simulation of the signal. When an AI writes, "The coffee is too hot," it is not reacting to heat. It is reacting to the statistical likelihood of the word hot, following the word coffee. When you close the loop and train AI on AI, you create a closed system. You cut off the input of fresh, low-entropy information from the real world. According to the laws of information theory, the signal must degrade, the noise must take over. This is the aha moment. We often fear that AI will become so advanced it will leave us behind, that it will transcend biology. But model collapse reveals the opposite truth. AI is parasitically dependent on us. Without the constant, chaotic, messy stream of human experience to ground it, the AI hallucinates, drifts, and eventually goes mad. We are the anchor. We are the source of the variance. We are the only thing keeping the digital mind from dissolving into a beige fog of statistical averages. There is a concept in the field called the warm pool. It suggests that to keep AI models healthy, they must always have access to a pool of warm, fresh data generated by living, breathing humans. We might see a future where human-created data becomes the most expensive commodity on Earth. In a world flooded with cheap, perfect, synthetic text, the typewritten, emotionally charged, factually sporadic blog post of a real person becomes a jagged diamond of precious entropy. So, what does this mean for us, the users, the humans? It means that the dream of a self-sustaining, self-improving AI singularity, where machines build better machines forever, is likely a mirage. There is a tether. The machine can wander far, but it cannot cut the rope. It forces us to reevaluate the value of our own contributions. We are told that AI will replace creative work, that it will replace writers and coders, and in the short term, for the mediocre tasks, it surely will. But in the long term, the system needs the creators. It needs the people who break the rules of grammar. It needs the people who invent new slang. It needs the scientists who discover facts that contradict the previous textbooks. If we stop creating, the AI stops learning. If we stop being weird, the AI becomes useless. This deconstruction of model collapse serves as a stark reminder of the limits of simulation. You can simulate the style of a Van Gogh painting, but you cannot simulate the life of pain and light that drove him to paint it. The simulation can copy the artifact, but it cannot replicate the source. As we move forward into this synthetic age, we have to be the guardians of the real. We have to value the friction of reality, the imperfections, the outliers, the tails of the distribution. That is not just noise to be filtered out. That is the signal. That is the humanity. And as it turns out, that is the only fuel that keeps the engine running. When we look at the black box of generative AI, we see a mirror. And right now, that mirror is clear and sharp because it is reflecting us. But if we step away, if we stop feeding it our reflection, the image will not evolve into something greater. It will simply fade away. The technology that feels like magic is, in the end, just a very sophisticated way of remembering who we are. And if we forget that, the machine forgets everything.
You've been listening to First Principles. Until next time, stay curious.